So, about the paper, thank you for reminding me. I would like to start with a brief discussion on this paper, and then I give the word to Seper. Seper is correct, yeah, for a short presentation on carbon-free material for construction. But before that, I want, as I said, to discuss this paper here. Just 1 second, I forgot to share the screen. Okay, very good. So who wants, I'm not sure if everybody of you was aware of this kind of informal homework. I suggested to read a paper that focuses on extreme wind estimation for the Strait of Messina. It's a paper that was published 32 years ago on the Journal of Wind Engineering and Industrial Aerodynamics, and it presents some methodologies that were used to find an estimate for the extreme wind speed to support the preliminary design of the Strait of Messina Bridge. I think it is an interesting paper because it clarifies how to move forward for estimating design variables with limited information. And I think it's also a nice reading because it shouldn't be too difficult and maybe a good training for reading scientific papers. Who wants to take the word? Maybe you to introduce, to say something. What is your take or whatever you want to say?
Yeah, in short, you can say that in this paper, the highlighting comparison that the paper develops is between two methods to establish the extreme wind speed. In particular, the correlation analysis and the simulation analysis. And I noticed that the paper agree with the correlation analysis design because it's more reliable than the statistical one. When we study, of course, the extreme wind speeds. And the main purpose of this method is to assess preliminary verification of the correlation between the anemometric measurements of the different stations that they considered near the Strait of Messina. In particular, one that is called the Punta Faro, that is maybe 2 kilometers far from the Messina, from the Strait of Messina. Talking about the simulation analysis, this is more based on a model, medical simulation analysis that use a code called the WINDS, wind field interpolation by non-divergence winds. And this model is based on the principle of mass conservation, so it's a mass consistent. And it's initialized with a wind field estimated from previous data, so that recorded in the ground level observation. And so we can say that this model is so unique. Because it produces a little bit different data from the different stations in terms of wind speeds. With respect also to the correlation analysis that uses the anemometric stations. And the main limitation is the definition of the physical restraints. So the strength considering the physical parameters around I was talking about the wind speed that may influence the construction of the design of the bridge. And so making a final comparison, we can see that the results of the simulations could be improved for sure. For example, by reapplying the mean codes of chemical analysis using a technique called the room technique, which consists in simulating the separation between zones of the zones, of course, around the strait, and modeling the occurrence of internal boundary layers. So we will have a more refined statistical criteria for this approach. An important thing that we have to mention is related, of course, to the correlation analysis that analyzed the orientation and the direction of the wind speed that interested the strait. In particular, they noticed, we developed this approach, this analysis, that the strong winds come from southwest and south, in which we have two important kinds of winds in Italy, the Scirocco and the Adaptation. And this is important because if we want to make a comparison with, I don't know, the northwest direction, we can observe that the frequency is so low. In particular, they analyzed specific months period, that is the winter. And so that's all.
Okay. And what are the values? Are they similar between the two methods, or?
Okay, the correlation analysis, you developed some measurements in the middle of the bridge, in the middle point of the bridge, and they observed that during the years, in particular, the wind speed at the middle point from southwest, west sector and the northwest sector increases around from 5 to 10 meters per second.
Okay, so let's make some considerations first of all. Reading scientific papers, I believe it's an important skill that you should acquire, because not only when dealing with climate change, but also when dealing with modern new technologies or technologies in general, they are subjected to continuous innovation, and more than in the past, because not because people are smarter, but because there is an increasing opportunities for cooperation, and therefore this leads to a more global research activity, more collaborative research activity that is continuously proposing advances. And I think it is then important that you don't refer only to books, which are static by definition, but you refer to these more dynamic forms of communication. And typically, the traditional way of scientific communication is given by scientific papers. Things will probably change into the future. I am expecting something different, like some collaborative form of web publishing, something that allows people also to continuously update the results, because also scientific papers, they are a bit static. So, but for now, this is a good reference. First, keep into account that there are good papers and poor papers. And so a first kind of advice that I give to you is sometimes if you don't understand, it may be that it's the paper that it's not well written, or maybe the paper that is not very innovative. And therefore, you know, sometimes the authors write in a complicated manner, and use complicated models to deliver simple messages. And this is one thing that it's a bias that is induced by the scientific competition and publish or perish policy or pressure. So there are good papers and poor papers. Of course, at the beginning, it's not easy to distinguish them. But the advice that I give to you, if you don't understand, maybe that you can also try to search for other kind of information. A way for recognizing good papers may be the impact factor of the journal, and which you can find in any journal. When you go on the home page, there is a mention to the impact factor. The impact factor is variable between scientific disciplines. It's not the only one indicator, because, for instance, on Nature, Nature has an impact factor that is, I think, around 50, which is probably the highest among all journals, but sometimes also in Nature I find poor papers. And but the impact factor is an indication. So in order to read a paper, of course, first you read the abstract or summary, and from the abstract you can already get an idea. A good abstract should explain the essence of the work and the results. So report the result. Sometimes you see that the abstract doesn't say really all of this, and here it's indeed reported. The results, the studies are based on two alternative approaches, each one constituting a verification and control element for the other, leading to sound and generally reliable assessments. And the final sentence says, we believe that this method can be applied also to other locations. The introduction should explain the why this work. So should explain what is the purpose of the contribution, and should provide some context, like we have a problem. The problem has been studied by author A, author B, author C, and give full references. So once again, we have a problem. The problem has been studied by Plinius, Cato, and Napoleon. And we propose here to a further advance to address the above research gaps. So we have a problem. The problem has been studied by Napoleon. There are still some research gaps or some unsolved questions. The purpose of this work is this, this, and this. So if you recognize a kind of train of thought like this, can be a little bit different, but if you recognize in the introduction a train of thought, so the introduction should be by definition quite easily understandable, it's already an indication of a good paper. If in the introduction you get puzzled, it's not a good indication for a paper, because you are not a real, long-term expert, but you are an educated person with some background in the topic, and therefore you should be able to understand it. If you don't understand it, it may be a problem. Maybe the paper is not very good. So here, for instance, says the design construction of the bridge over the Strait of Messina requires an accurate and reliable study of wind speed. So this is the problem, okay? And then here it describes the data, fine. They say, we have anemometric stations, and but at this station, the amount of information is insufficient. So this is already outlining a gap, okay? Italian Air Traffic Control and Communication Board and Enel, National Electricity Board, weather station in the area around the Strait, supply data recorded over much longer time periods, but are very far from the site. Again, a problem, okay? In addition, these stations are positioned in locations which are too dissimilar, another problem, so that the information collected cannot be used without any prior accurate conversion. It's very clear, okay? Unfortunately, it happens that the extreme orographic complexity of the area under examination renders the classical conversion procedure unusable, another problem. In fact, the commonly used theoretical models often fail when dealing with this conformation of the ground. Okay. Moreover, topographic wind tunnels do not guarantee sufficient reliability. Another motivation, another problem. Okay. In the light of these observations, so all the problems, bearing in mind the need for a study of high reliability, a coordinated research project was started, and we participated to that. So it's describing what they do. And this collaborative project is based on the use of two alternative methods. So this is what we do: correlation and simulation. Each of the two acts as a verification and control for the other. The correlation analysis provides a preliminary assessment of the existing correlation between anemometric measurements recorded at Punta Faro and those recorded at other stations in the area during the same period, which means that they explain that Punta Faro, they have measurements, but they are very short. In the other location, they have longer measurements, but the other locations are very far. So the idea is I studied the relationship between Punta Faro and the other locations, and then I extend the record of Punta Faro to the observation period of the other location. This is the idea. I think it is very clear. The simulation analysis, which was carried out by blah, 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 makes use of a preliminary implementation of a wide range of numerical models of the strides or its parts. On the basis of these models, the measurements taken by the individual stations are transformed into wind speed of the bridge. So there is no consideration of Punta Faro. They just take from other locations, or maybe there is also Punta Faro, but in any case, what they do is not to study the correlation, but to use the observations to build a model that gives directly the speed over the bridge. Of course, what they have two alternatives, and they want to compare them. Okay? This paper provides a synthesis of the methods. Here, with respect to what I said before, it is missing the reference to the previous literature, because probably there is no literature on the wind of the Strait of Messina. So they describe the data, which is fine. Okay. Sometimes the data description is reported in a separate section, like here, actually, weather stations and data recorded. And here they explain the data that they recorded. Here, I think the table is the list of the weather station with the observation period, you see, and that's it. Look at the observation period. This is another thing that I always do. It's quite short, okay? Given that we are interested in very extremes, it is a bit short. Okay, and then here there is the map. Fine. And the data required in each station are processed and corrected according to the procedure, and they make reference to a paper. And then there is the correlation analysis. It explains what they did. Okay, it is quite easy to understand it. This is a cumulative, I think it is a density actually. No, it's a cumulative because it's in the different months, sorry. So it's cumulative probability of wind speed higher than 15 meters per second recorded by the Punta Faro anemometer 92 meters above sea level. There are different curves for different directions. Good. Because wind, it's not just the measurement is velocity and direction, okay? Okay, and then there is a description of the winds and statistics. Here there is a weather map, a wind map, and I think there is also, no, there is no wind rows here. And then there is the numerical modeling, the explanation, they explain the code, etc. And here there is, I think it's the orography, the numerical modeling of the orography. This is like a weather model that they apply, like a climate model, but refers to a small small surface. Climate models usually work all over the world. This is a regional model. Okay, and then this is numerical modeling of the ground roughness. And here is the wind field and simulation analysis. Okay, it is described. There are, I think, there are not too many equations, so I think it is not difficult to read it. This is a representation of the windrows in several stations. If you are not familiar with the windrows, given that you are working on offshore engineering, I think you are already familiar. But in any case, if you are not, just try to improve your knowledge. The windrows provides probabilities of wind velocity in the different directions. It's very easy to understand it, but to explain it from the start, it takes time, so I skip it. And if you don't have a good knowledge, just go on Wikipedia, windrows, and it is perfect. But basically what you see here is for each direction, the probability of wind velocity. And here it is. Let's go to the estimate. Here you see return period and wind velocity. So this is in meters per second, okay? So you see that for, let's see, 100 years, we are around 45. And this is, let me see the caption. Probability distribution of maximum annual value of VP corresponding to Salina, Messina, Reggio Calabria. Okay, perfect. And let's see here, 100 is 100 return period is 35, and here it's 35, and here 100 years is 40. For the bridge, I think they need 100 years of return period is not enough. I think they need to refer to at least 1,000. Anyway, keep in mind these values because those of you who are attending the lab, or in any case, I can give you the link of the slides. Tomorrow, the other teacher will show how to download future climate data of wind for the Strait of Messina and how to get the same estimates that you see here in the future climate. When you compare ground observations with climate models, it's a bit tricky, and he will explain to you tomorrow, or as I said, I give you the link and you can go through the slides. He will explain why the values that he will extract under climate change are lower than those that you see here. Not much lower, but a bit lower, okay? He will explain that. Okay, and here you see the extreme mean wind speeds at the bridge center line from the simulation analysis. So, okay. Salina, Messina, Reggio Calabria, Catania, Cozzo. Okay, and this is the estimate VP for 41 meters per second. 41 meters per second is about 150 kilometers per hour. Okay. Okay, and then let's see if there is a comparison. This is the windrows, I think, for the bridge center line. And no, it's there is the results are simulation. Just 1 second, I want to see if there is the result from correlation. Probably it's reported later. Let's see conclusions. The conclusion is another important section for obvious reasons. Some of the papers, it is something that I don't like, report a long section on discussion, and then the conclusions. So if there are 2 sections, you have to read both of them because discussion is also important. Okay, this paper summarizes the procedure established for evaluating the average speed of the design wind, and there is substantial room for improvement, and the agreement between the correlation and simulation analysis is excellent, with reference to the south northwest winds, acceptable for northeast, and the differences between these two directions, although not meaningful for the design of the bridge, deserve further evaluations. And that's it, basically. So you see, it's not, it's fine. It's not so difficult to read. Okay. Yeah.
I don't know, Anne decided to install other stations for surveys and maybe for the strikes of the Messina Bridge. These stations can be used for surveys or any measurements.
Maybe this paper was published in 1993, so just 10 years, 12 years after the Ustica disaster. So probably if there were data available, they didn't consider them because the observation period was too short. Maybe that today there are additional data available. Actually, I tried to search on the web and I didn't find anything but these two papers, and the other one is in Google Scholar. This is the more relevant. Maybe that looking, because if they have measurements, I'm not sure if they made it, if they make them public. Maybe that trying to look at the website of ISPRA. ISPRA is the National Agency for the Monitoring, for Environmental Monitoring. Maybe that there is something. I didn't inspect in detail because, and also maybe if you look at the climate data store of Copernicus, maybe that they have some observations. Usually they present gridded data. Gridded data means that they take ground measurements and then make an interpolation in order to be able to have a complete coverage of the whole globe. So I am quite sure that they have observations, but and these observations may have profited from additional stations that were installed after the Ustica's disaster. There is to say that it would be better to have access to the raw data, not gridded values. But I'm not really sure if they are available. I don't, at least with a rapid search, I couldn't find them. Because, sometimes the data are proprietary data and are not accessible. You have to pay for getting them. Maybe that there is something available. Yeah, that is to say that the final project of the bridge is still to be developed. And I'm sure that when they will go to the final design, they will take into account everything is available. But for now, the preliminary project or the intermediate project is the same project that was approved in the 90s. So I think that the estimates that you see on the web now for the website of the Messina Bridge Company, I think their information is the same information of 30 years ago with some updates in 2011, but not, I don't think for what regards the wind speed. Okay. Okay, so anyway, I think this is indeed interesting, and who is attending the lab, you will get something more. If I forget to send you the link for these slides of the lab, because they are, I mean, they are short, and I think they are interesting. So if I forget, send me an email and I'll send it to you. Okay, very good. And by the way, the link is here. I'm just recollecting. If you go on my website, and you go the lecture note, you go to the lecture notes of the laboratory. Here there is a link. I think it is this one, the third. Let's see. It is a link to a Google Colab slide. And I only recently learned about Collab. I think it is excellent because it allows also to run the codes. By the way, so I understood that it's a better option if you want to run codes in Python to run it in Collab. Yeah, as you probably told me last week. You said Jupyter. You said Jupyter, yeah. And so basically here you see that there are all the codes that you can run for installing the libraries and finding the data. And here there is a map of wind speed over the Strait of Messina. This is taken from a climate model and developed the graph by running this coding Collab. It is very simple. You may just run everything here. And here there is an estimate of wind speed. And you see that this is regional average and Messina. And you see that the speed is lower. This is in meters per second. This is basically not an extreme, but if also we look at the extremes, they should be somewhere here. Tomorrow he will introduce everything. This is a daily max wind speed. And you see that it's, the max from 1950, because these are data collected from a climate model. They cover only from 1950. But you see that it's around 20, something like that, or maybe less. But I think there is an estimate here. Everything is produced, of this figure is produced into Collab. Figure show, let me see, what is this? It's annual maxima. These are annual maxima from 1950 at Messina, and you see that the magnitude. And here there is an estimate, the histogram of the annual maxima, so then basically the density distribution. And then there is here one second, because okay, perfect. And here there is the annual maximum wind, and this is the return period. This is empirical distribution, so the return period is only limited to the length of the time series. But here there is the GEV estimation, it's a probability distribution. And let me see if there is the value for 100-year return period. I don't think so, because probably he still has to develop the computation or the slides. Anyway, this is the link. You find it in my website, so there is no need to write to me. Okay, perfect. So now I give the word to Seper for the presentation. Okay, yeah, okay, just 1 second. Okay, you know that you have 5-10 minutes. You can come here. So there is the micro, they can listen to you.
Good afternoon, everyone. I want to tell you about the environmental impacts of sulfur concrete. Why sulfur concrete? Respect to CO2 emission. First of all, I want to introduce briefly about the concrete. After the water, concrete is the widely used material in the world. And the concrete equals to combination of aggregates, water, and cement binding. But if you want to produce per ton of cement, it releases 4.9 tons of CO2. The cement industry is responsible approximately around 8% of CO2 emissions. Now you can see the concrete and the cement industry, how much they can produce the CO2 emission. But now, why sulfur concrete? Sulfur concrete is a concrete where sulfur acts as a binder instead of the cement. The unique properties is the rapid setting, high chemical resistance, and recyclability. And cement production contributes, as I told before, cement production contributes 8% of global CO2 emissions, but high energy consumption in Portland cement manufacturing and restores deflation, like limestone quarrying and water usage. And advantages of sulfur concrete: low CO2 footprint, because sulfur binder avoids any cement production emissions, and rapid curing, reduces energy for heating or steam curing in the cooling weather when we construct the concrete buildings. And the last one is chemical resistance. Why? Because for this reason, less degradation, longer lifespan, and finally reduce the material usage. And the source of sulfur are often byproduct of petroleum and natural gases industries. Utilizing industrial sulfur prevent waste disposal issues, and it's very helpful for the environment. And supports the circular economy by recycling industrial waste. And positive environmental impacts of using sulfur concrete. Lower greenhouse gas emissions compared to Portland cement concrete. And the other one is waste reduction by using industrial sulfur. And the last one is potential for reuse and recyclability of sulfur concrete, because we can melt it and reshape it. And the negative impacts of the environmental impacts of the sulfur concrete. Sulfur production, if not a byproduct, can be energy intensive. And the other one is the potential leaching of sulfur compounds if improperly handled. And the last one is limited long-term environmental studies compared to conventional concrete. Life cycle assessment, or LCA. Sulfur concrete generally shows reduced global warming potential and lower energy consumption in production. And the last one, extended durability reduces maintenance, demolition, and reconstruction impacts. The sustainability of the sulfur concrete. The first one is ideal for chemical plants, industrial flooring, and marine structures. The second one is can contribute to green building certification, like LEED and BREEAM. LEED means leadership in energy and environmental design, and BREEAM is building research establishment environmental assessment method. And the last one is support sustainable infrastructure with long service life and minimal environmental footprint. For the conclusion, sulfur concrete offers significant environmental advantages over conventional cement concrete. And the two is challenges remain in large scale adoption and long-term performance data. And the last one, for the future research, it's better to optimization, environmental monitoring, and wider industrial applications. It's
Any question? Yes. So, why it is not widely used? The questions.
yeah. Because it needs some equipment to heat the sulfur, make it from the solid to the liquid, and it can combine with the aggregates and some additive materials to produce the final production as a concrete.
And you know, if there's been invest information on the carbon cycle of electricity, because I understand that it releases less carbon. If there is some CO2, it releases for the large. So it's still it is CO2 less expensive than CO2.
What excellent.
If you need a lot of energy to produce it, energy means CO2 emission.
Yeah, exactly.
Okay, so still the overall use of CO2 is.
Yeah. Because Professor, the energy we want to use this one is more less than the energy we want to use to produce the cement. Because we use more energy for produce the clinker, and after the clinker, you produce the cement.
And I have a final one. What are alternatives? So I don't think this is the only alternative of concrete. I don't remember if this was mentioned by the lady presented last week.
No. She tells about sonocrete.
Okay.
Yeah, sonocrete, it's another type of concrete. They use the cement, but they use the less cement in their in the mixture design. They use ultrasonic technique to make the concrete. Yeah.
Hey,
Yeah.
thanks.
You're welcome.
Good. Thank you, sir.
You're welcome.
We dedicated less time because, I just wanted to be very brief with this. Okay, now let's go back to risk then. Okay, and good. Okay. Risk-based adaptation design. As I told you, we skipped a couple of links, okay? We did introduction, case studies, Strait of Messina, climate impact, and then we skip 2 links and we go to risk-based adaptation design. Okay, very good. So, as I said, we start from this formula. So risk, we define risk as a measure of the expected damage during an assigned time period given by an expected event. So I make an example. We define risk as the damaged in a year, average damage within a time span of 1 year due to earthquakes, okay? Or I define risk as the average damage expected for a duration of 1 year for a flood, the occurrence of a flood. So it is expected damage, okay? Usually the damage is measured in monetary units. Once again, let's say that we don't focus now on the loss of human life. We just focus on the loss of assets, goods, etc. And therefore the damage is convenient if we measure it with monetary units. Like on average, in the time span of 1 year, I expect in Ravenna a damage of 1 million due to earthquakes on average. This means that you may have no damage for 50 years and then a single earthquake that causes a damage of 200 millions. And then in the long term, you should compute the average. The average by definition, either it's given by an analytical relationship on the basis of a theory, or you can measure it through observations. Okay, so for instance, if I flip a coin, I can estimate. Flip a coin is not a good example because there is no average. But if I toss a dice, there is an average, which is, if I'm not wrong, is something more than 3, correct? Yeah, it should be, because 3 is the average between 0 and 6. Between 1 and 6, the average is 3 point something, okay, 3.5. So I can just derive the estimate analytically, as I did. So what I did is an analytical derivation basing on a theory. Or I could take a dice, toss it, and then I make like 20 trials and I compute the average. But of course, in this second method, you need a long time span. The same for risk. You can measure risk like Ravenna. Every year, I record the damage in millions of euros given by earthquakes. So 0, 0, 0, 0, 0, suddenly 70, and then 0, 0, 0, 0, 0, suddenly something like that. So it's an expected is a correct way to say average, okay? The average is defined as the expected value. It is the expected value. Basically, the expected damage during an assigned time period, it's essential that you define the time period. Okay, in 1 year, or in 10 years, or in 100 years. Okay, and it is then measured in this case, as I said, in monetary units. That's fine. You can understand why I excluded the loss of lives, because it is a bit bizarre from an ethical point of view, okay? So some people say, don't use monetary units to quantify the value of people. Actually, insurance companies do that. But let's for now forget about the life of people. Okay, and we define this expected damage in a given time period for a given event as the product of probability during the given time period of the event. Okay, like earthquakes, probability of exceedance of an earthquake of magnitude 3. Of course, you have the full range of probabilities. So probability, vulnerability, and exposure. Okay.
Vulnerability and exposure is not synonyms.
No, absolutely. Two different things. We are explaining it. Probability, it is often called also hazard. We measure the hazard with the probability. And this is why, keep it in mind, it's a completely different story. We talk about hazard and risk, okay? So when you see the media mentioning natural hazards, it means natural events, and they refer to the probability. Okay, when you talk about risk, there is something more that comes into play. So the hazard is given by, as you see here, the probability of the considered event to happen in a specific context and the assigned time period. So for instance, let's refer again to the earthquake. Probability that in 1 year you get an earthquake with magnitude more than 3. Okay, and then what are vulnerability and exposure? Okay, vulnerability is the probability that the system, so a given societal asset like the city of Ravenna, is damaged at a certain level if the considered event occurs. So basically, if I say that vulnerability for a given earthquake in Ravenna is 0.5, this means that I have a probability of 0.5 that I get a damage corresponding to the exposure. Okay. Third thing, exposure It is, let's suppose that the event occurs and vulnerability is 1. So what is the value of the damage? Okay, so let's suppose I get the earthquake of magnitude 6 in Ravenna. Let's suppose that vulnerability is 1, so there is no protection. What is the damage that I get? And this is the exposure, okay? And it is measured in monetary values because, of course, I said the risk is expressed in monetary units. P and V are probabilities, so it's dimensionless. And the exposure, it is something that first is varying from 0. It's a monetary estimate of the damage. So it's something that goes from 0 to infinity, or not really infinity, okay, another philosophical discussion, but let's say goes from 0 to the total value of the assets in Ravenna. Or you may refer also to a single building, like the exposure is the value of the building. Let's suppose that the building is destroyed, okay? And then you have the value of the building, like 10 million monetary units. Okay, and then you can easily understand that if P is the probability of the event occurring in 1 year, P is the probability that the building is destroyed, E is the value of the building. The product of the 3 is precisely the expected damage in 1 year. Okay? And of course, you get the full damage, probability is 1, so the event occurs. Vulnerability is 1, so the probability that the building is fully destroyed. And then you get the damage corresponding to the value of the building, okay? And you get this damage every year, because every year the probability of occurring the event is 1, and every year the vulnerability is 1, every year you get an earthquake, every year you restore the building, reconstruct it, and you get this expected value of the damage every year. But of course, the event doesn't happen every year. The building is not fully destroyed. So you can interpret vulnerability also as the fraction of E that is indeed lost if the event occurs. Okay, you can interpret vulnerability in this way. Like with an earthquake occurs of magnitude 5, half of the building is destroyed. Vulnerability is 0.5. Okay? Because this is the same meaning as the probability that you get the full damage, the full building destroyed. It is very simple, and indeed this is a definition that has been developed at the international level. It's, there are some additional factors that may be considered, like, for instance, some people want to highlight the value of preparedness of the population. And therefore, they include here another factor, which is preparedness. If you don't include it, preparedness is including vulnerability, because preparedness allows you to reduce damage if the event occurs. Like, why do we teach to the children how to behave in case of an earthquake? Okay, this refers to protecting our life, but you can easily transfer the concept to any damage, okay? So preparedness, if you prepare people, the civil protection, how to behave properly, of course, damage is reduced. And in my opinion, can be considered part of vulnerability. But some people want to emphasize the value of preparedness, and therefore they define vulnerability as a technical vulnerability, which doesn't take into account the preparedness of the society to react, and introduce a fourth factor, preparedness, because they want to emphasize that if the preparedness is influential, I find it a little bit, I mean, it requires a careful consideration, because is preparedness, if you introduce preparedness as a factor, varying from 0 to 1, for instance, it means that you assume that if the population is fully prepared, they can really annihilate, bring the damage to 0. This is not always possible. So you have to consider the kind of event. And what in some of the cases, yes, preparedness may help you to fully avoid consequences. In other cases, preparedness may not reach the value of 0. Okay, so it requires a careful consideration. I think this is very simple and easy to be understood. But of course, now we have the three questions: probability, vulnerability, and exposure, how to estimate them. And there is also one thing to say that usually in the literature is not considered. Vulnerability and exposure depend on the probability. Because, of course, if you have an ordinary extreme, you may be safe because you are not vulnerable. But when you get the same event with an higher magnitude, then vulnerability changes. So for changing probability of the event, because of course the more frequent the event, the less the intensity. So if you increase the intensity of the event, it means that probability is reduced. And therefore it means that B depends on probability. So this relationship between these three factors is not adequately considered. And the same for exposure. It depends on the probability. Because think of a flood. If you get a very extreme flood, there is a large area that is drowned, and therefore a large damage, a large exposure. If the flood is very small, even if there is flooding, there are only a few buildings that are interested by the flood, and therefore the exposure is lower. So it's interesting to analyze this relationship between probability, vulnerability, and exposure. Now, let me say, before we go to the estimation of these three factors, let me say that let me discuss the issue of the human life. So there are some contributions who suggest not to put everything together because they believe that, and this is reasonable, when the life is at risk, the procedure and the design procedures should be different from the situation with respect to the situation where only money is at risk. Indeed, this is true. I mean, as an engineer, you realize that if the risk is money, is one thing. If the risk is the human life, is a different story. And indeed, you may be accused of homicide, is the word in English, if in Italian is omicidio colposo. It means that you, without a direct will, you wanted to kill a person, and this doesn't happen with. It is a criminal offense, and instead, if it's only money at risk, it's a civil offense. It's a completely different story, completely different legal procedures, and therefore they say, look, let's try to keep them separated, even if it is in principle possible to monetize the human life. This is what the insurances do, but it's a different story. They monetize it not in order to protect the people, but to just reimburse the damage. So it's a different story. Basically, the insurances, they monetize the life by assuming that the life is lost. If you instead do something to avoid the loss of lives, it's, translating into a monetary value is something that needs to be done very carefully. So I don't think it would be a good idea to, in the engineering design, to monetize the human life. It's just a different situation. And therefore, also when we estimate vulnerability and exposure, if the exposure is the human life, also vulnerability has to be estimated in a different way. And so I think this is an interesting consideration to be done, because it's true that the insurances do that, but it's a different purpose. They are not in charge of protecting people. They are in charge of reimbursing a damage once the fact has occurred. So it's a different story. Okay, so how to estimate them? Let's start from exposure. Exposure is probably the easiest. It's given by the value of the good, and it's the easiest, but still is a bit complicated because it's not only you have to first. It's not only estimating the value of a good. It's you have also to identify the goods, and therefore, depending for different magnitudes of the event. For instance, I'm used to do that for floods. We assume different flood values, and then for each value of the volume of water that overflowed, that formed the flood water, the volume of the flood water. For each value of the volume of the flood water, we estimate the area. We map the area reached by the water, and then the buildings, and then you have to estimate also the velocity, because what makes a flood impactful is more than the water depth, is the water velocity. So you may have even a limited depth, but with high velocity, it's a problem. So it's not only depth, it's more the velocity of it, of water. And therefore, we identify the area that was interested by the flood, and we map the buildings, and then we estimate it. It's an activity that is becoming, unfortunately, very frequent, and there is a lot of research in the mapping of the flood, and also in the estimation of the damage, because, of course, sometimes you need procedures that can be applied over large scales. And it's also interdisciplinary, because it's not only engineering, it's also economy, and also in some of the cases, the damage may be a physical damage, and therefore, I mean, the life is excluded by monetary evaluation, but the trauma, for instance, is included, and we have also to estimate the trauma that may be derived, and also think of cultural heritage. Cultural heritage is really threatened by extreme events, but how to monetize it? This is a recognized problem. So a famous painting is a big problem for Florence, for instance. And if you get an earthquake and some paintings are lost, or some historical buildings collapse, what is the value of an historical building? It's difficult. It's very difficult, because also cultural heritage is intangible in some of the cases. You cannot really quantify it. It's also a kind of personal affection. If you lose your references, like a church like think of Bologna, Piazza Maggiore, if the church collapses, some people feel like their identity is lost, and this is indeed not easy. Vulnerability requires a careful consideration of the measures of protection. So the seismic resistance of buildings, infrastructures, for instance, the levees of a river, are they safe, or the levees can be threatened? And you have to assign this number between 0 and 1 to quantify the chance or the extent to which you get damage if the event occurs. So in the case of floods, I take a value of the river flow, for instance, the value with 100-year network period, and I have to estimate the chance that the flow remains between the levees or not. And therefore, it requires a careful evaluation of all the measures that are in place. And then there is the probability. Probability.
We have some that we don't have, like some pre-cosmos, like we don't have dam to reserve the water. So in this factor, how can we, like climate change, rain, flood, how can we face these things in to measure the vulnerability assessments?
I mean, first of all, you are,
Like in my country, last year there was a flood. This year again there was.
and you don't have a reservoir upstream. Correct?
Yeah.
The country is Pakistan. No? Yeah, you don't have a reservoir upstream. Okay, so of course you should try to estimate the probability that you get flooded if a certain river flow occurs. This is what we do with floods. This probability is affected by the presence of the reservoir. If you have the reservoir and this reservoir is well managed, the probability is reduced because,
There is some places that cannot build the dam.
yeah, of course.
Places.
If you cannot, of course, you don't have any alternative, and you have to estimate the probability to get flooded if a certain river flow occurs. So the event is the river flow, or the event is an earthquake. And then, given that you get that river flow, what is the probability that your home or your city is flooded? And if you don't have a reservoir, of course, there is no alternative. You have just to refer to what is in place. Or you may refer to a reservoir if you have the opportunity to build it. So if the question is, how risk is modified if I build a reservoir or not, my answer would be the event remains the same, which is the river flow with a certain amount of cubic meters per second. The event remains the same, P remains the same, it's vulnerability that decreases. And how much it decreases, you have to set up a model that predicts the chance of overflowing the levees if the reservoir is there or not. And we have hydraulic models to do that. But of course, this is possible if you have the opportunity, if you have the alternative. If you don't have any alternative, the reservoir is not there. It's, of course, there is no question. Often there is this question, for instance, here now we are discussing if or not build a dam upstream my city. And there is the question, like, what would be the risk, the flood risk with the dam or without the dam? Keep in mind that if the reservoir is badly managed, vulnerability may also increase. Okay, and because you know the reservoir, the purpose of the reservoir is when the flood comes, they should store part of the water. But let's suppose that the reservoir is full and the flood comes, and they try anyway to store some of the water, realize that the dam may overflow, so the only reaction that you have is to release a big amount of water, larger than the water that would have been released without the reservoir. This may happen. Okay, here, when I describe estimation of probability, I also report an informal introduction to probability, which we already discussed, because it's what we discussed last week. And it's the same thing with a bit of different examples. There are some R codes, which basically are those that we used in Excel. And but you can skip it. If you feel like it's clear to use the concept of probability, just skip it, okay? Okay, and you see here continuous random variable. Now, very interesting. There are some probability distributions. Let's relationship between P, V, E, and R. Okay, just 1 second. I want to see, okay, here I have only one graph. Okay, let's use this. So let's focus on exposure. And let me first explain this graph here. first of all, what is in the horizontal axis and what is in the vertical axis? In the horizontal axis, you have the intensity of the event. You could put there also, instead of intensity, return period or probability. The intensity is increasing for increasing return period. So the substitution of the intensity with the return period is very easy. You just remove intensity and put a capital T here, okay, and the graph remains valid. If you want to put probability here, it's a bit different story because intensity increases for decreasing probability, and therefore you should flip the axis. So let's suppose that here you have intensity, or if you like more, return. On the vertical axis, focus only on exposure, the blue. We have the exposure, the damage. What can you see here? If you only look at the blue line, if you only look at the blue line, you see that for increasing intensity, you have exposure 0 up to a certain level, which means that even if you get flooded, the flood is so small that you don't get any damage. Typically, this is the situation of the floodplains. There is the floodplains are a belt around the river where you don't build anything. You just keep the space there for allowing the river to flood. So the river floods, occupies the floodplain. There are no buildings, nothing, so no damage. For increasing intensity, you have an increasing exposure. This is just a pattern by chance. You can draw any pattern here with the only condition that the blue line is non-decreasing with increasing intensity, because it's unreasonable that you get a damage that decreases with a huge flood. Okay, but this could reach a max. I mean, the exposure of the blue line could reach a max and then be completely flat, because of course, up to a certain magnitude, you don't get any more damage anymore. Everything is flooded, everything is drawn, and that's it. Okay, this is just a pattern that I put there for basing on my imagination. Okay. Okay, let's forget now about the blue line and the orange line. We never considered it so far. Let's focus on vulnerability. Vulnerability is, again, you can plot it on a different scale, of course, on the vertical axis with a different scale, because it varies from 0 and 1. Vulnerability may say 0 up to a certain intensity of the event. This means that up to a certain earthquake, I am not vulnerable. Even if the earthquake occurs, there is no damage to the buildings, because the buildings are all protected. They can resist to up to a certain scale of the earthquake. But then at a certain point, vulnerability increases. Of course, never gets greater than 1. It may get to 1, or it may not get to 1. Because even if a very disaster occurs, you never destroy everything. So again, this is a pattern that is drawn completely by chance. Okay, perfect. Now, let's keep on the screen the blue and red line. What happens to the risk? The risk is simply the product of the three. But on the other hand, the risk is one of the factors is probability, not relative period. And therefore, probability, if you put the numbers here below, it's decreasing. So it may happen that the risk, depending on the patterns on the other two lines, and depending on the pattern of probability, may be that the risk reaches a top to a certain level. Because up to a certain level, the event is so rare, it occurs only on average once in a million of years. And even if the damage is very strong, even if the vulnerability is 1, On average, every year, you get close to zero, the expected damage every year. So it may happen, and indeed, in many situations, it happens that it reaches a top. And this is a useful guide because if you want to make a cost-benefit analysis, probably the best solution is to design for an intensity of the event that is located just close to the max. Of course, loss of lives not considered, because of course there are situations where no, when there is only the risk of losing only one life, I don't want it, even if it's very small. I don't want it, maybe. And therefore you don't, because I mean, designing for the max means I accept the damage, and I accept not to be protected for a damage that may be larger. So it's like saying, I accept to lose like 10 people per year. It's fine. I don't care about them. So it's a bit, But if you just focus on the economic damage, this could be a reasonable solution. Of course, this is not a cost-benefit analysis. Be careful. This identifies the event that gives the max expected damage. And then, if you want to make a cost-benefit analysis, you have also to evaluate what is the cost of the measures that I have to build in order to so this kind of protection, this kind of vulnerability, this value of vulnerability. Okay, or what is the cost to intervene on probability? Intervening on probability when it is climate related is a bit problematic because you have to intervene on climate. Okay? Remember that the reservoir is vulnerability, is not probability. Okay? So this is an approach that could give you an idea, like what is the intensity of the event that gives the max risk. And this is very much pertinent when dealing with climate change, very much appropriate, because when dealing with climate change, when studying the adaptation, when studying this procedure for adapting an infrastructure, we have to be aware that the solution has to be sustainable, and therefore you cannot, get protected against something that has a very low probability of occurrence, because it means doing nothing. And this is what happens very frequently today. We don't do anything because people say, yeah, but to solve this problem with the future climate, the climate models tell me that the future climate is very bad, and to get fully protected is very costly. Who pays for that? Who is responsible for that? And then nothing is done. So in climate adaptation, climate change adaptation, it's very important to be able to find solutions that are sustainable. And this could be a good idea, okay? But keep in mind that to estimate exposure, relatively simple. To estimate vulnerability, a bit more complicated. And future probability, much more complicated. You need models. And for exposure, the models are maybe quite simple, are socioeconomic models typically. For vulnerability, they are engineering models. And to some extent, they can also be like socioeconomic, think of preparedness of people. And for probability, we need to answer the famous question, what is the future climate? Okay. And I'm stopping here today. Just keep in mind that this is one of the central themes. It's not difficult, as you see, but this question, risk equation, is a question that maybe is very likely to your exam. And you have also to be able to explain, to redraw this graph and to explain why there are these patterns. Okay. Questions?
That's better we see like we saw before. they estimate the exposure to the liability probably with a different magnitude because the models that we saw the code.
Yeah, there are models to estimate different extreme earthquake, extreme wind. The most relevant things are not related to the sea because you know it's a suspension bridge, so it's there is no problem with the waves. The most relevant things are wind speed from an environmental point of view and earthquake. And wind speed probably more concerning than the earthquake because it's more subtle. I mean, it's also related to the possibility to cross the bridge with trains, which they have very little tolerance with respect to, you know, waiting, oscillations. Trains have very little tolerance. Cars is much, they are more tolerant. Okay. Perfect. Next week, I'm not teaching. I am in China, and we will see each other in 2 weeks. And for the lab, tomorrow there is lecture. Next week, I'm not sure. There is lecture for the lab next week. I'm not sure. Okay, anyway, you can check in the timetable. Okay, thank you very much. And if you have any questions, feel free to write me emails.
Thank you.
Thank you very much. Bye.